Hi, I'm going to start this fourth and final video by reminding you what one of the key takeaways so far for me has been in this research on group decision making. So if there's nothing else you came away from this first couple studies with, it should be this. Information exchange can increase belief accuracy when everybody contributes equally to the communication process. Right? So I want to acknowledge that all of this research, and this includes not only my own research, but a number of other studies supporting this argument, all of this research has studied numeric estimations. So when I say numeric estimations, I mean things like, we talked about examples like how many units of this product will sell next year? What is the probability that some patient has heart disease? What percentage return will I get on my investments? And this includes a lot of the decisions that we might make, but it's in fact not often how we make decisions. At the end of the day, we often make decisions as a binary choice. We start with saying, what's the return on my investment? But then we just ask, should I invest in it? We might say, how productive will this employee be? But then we just ask, will I hire them? And it turns out that things look very different when we move into the binary choice space instead of just looking at numeric estimates. Now, this might not seem to be true at first glance if we were to look just at research on the collected intelligence paradigm. It would tell us that everything works fine for binary choices. If you're just aggregating independent people, it's great. So one really powerful example comes from that physician example. So when you aggregate the opinions of a whole lot of physicians who are determining whether or not a person has cancer, it turns out not only do you get a better estimate from the aggregation of the group than you would by just asking the most expert person within the group, but we also have theoretical research showing that aggregating a whole lot of estimates produces similar results whether you take an average of numeric estimates or whether you take a vote on something like a binary choice. So in this collected intelligence space, there's no reason to think that things would look different. But it turns out that when we study this problem in a dynamic setting, so in that paradigm where people form estimates, influence each other, and then revise their estimates, binary choice simply ends up amplifying the majority belief. So we can look at this in two kinds of scenarios. So in the first scenario, we think about a case where people form and exchange binary votes. So that would be something like a committee meeting where we just ask from the beginning, do you want to hire this person, yes or no? We each form a private belief. We then maybe take a vote. We all raise our hands if we want to hire that person. We all get to see what other people think. And then maybe we revise our beliefs after seeing what other people think. All this does is ends up amplifying the majority opinion regardless of accuracy. And it turns out this is true even if there's a correlation between confidence and accuracy. So you might think, okay, the problem is that people are only able to observe each other's binary votes. That has less information, right? We know that letting people learn about numeric estimates improves. So maybe you think, if possible, I'll have people form and exchange some kind of numeric estimate before voting. So suppose we're a firm that only invests in new products if they'll give us a 10% return on our capital investment. So we sit around, we have a conversation, you say, what return do you think we'll get? What return do I think we'll get? And we all form some collective numeric estimate, and then we take a vote. Do we invest, yes or no? It turns out even that ends up amplifying the majority opinion when it comes to the binary vote. What's really remarkable is that we've found that groups can amplify an incorrect vote even at the same time as their numeric estimate becomes more accurate. So I'm not going to talk through all the mathematical theory behind this and the conditions that make it possible. I'm just going to illustrate this with one simple example. So suppose you have that investment decision and you ask a group of maybe a committee of 10 people and they all have their conversation. So what this figure here shows is how that distribution of beliefs looks. So every point here shows everybody's final numeric estimate about the return on the investment after discussion. And the lines show their trajectory over the course of the discussion. So if you see only a point for some people, that means they didn't change their estimate over the course of the discussion. So I want to highlight these two red examples on the chart. Those are two people whose estimates, initially the numeric estimates started below that 10% threshold. As a course of discussion, their estimates went above to, or at least on the 10% threshold. So they were people who moved from a no vote, they said, no, don't invest, it's not good enough, to a yes vote. They said, yes, invest, it's going to give us at least 10% on our return. And the key thing is that these are the only two people who changed the vote as a whole. The only people who changed the vote, people who crossed that threshold boundary. Now this example, even though those two people crossed the threshold boundary, the mean belief is decreasing. In this example, it goes from an average belief of 13% to an average belief of 12%. So we see that the vote and the numeric estimate go in opposite directions. So in this example, if the right answer were no, don't invest, it only returns 5%, then the vote would be getting less accurate, even as that average belief gets more accurate. So the important thing to take away here is that in the same group, in the same conversation even, the binary choice vote and the numeric estimate are decoupled. They're governed by different dynamics, and things that can improve the numeric estimate can decrease the accuracy of the binary vote. So what does that mean for us? What it means, first and foremost, is that collective intelligence is contingent on task structure. This simple question, even we started with, is social influence good or bad? And then we said, how do we let people communicate, numeric exchange or unstructured discussion? Even this question turns out to depend on whether you're structuring your task as a numeric estimate, or whether you're structuring your task as a binary choice vote. So what this tells us is that when we think about designing structures for groups, we actually have to think about two roles for groups in the collective intelligence space. One role for groups is to generate and aggregate information. So maybe you are a manager who's really concerned with coming up with a good sales forecast for next year. Then your collective group is going to be great at that. Let them talk to each other, use the optimization strategies we picked up in the first couple videos to get the most accurate estimate possible, but then you take that estimate and make a final decision with it. The group is not actually making a decision. The second role for a group is to generate a recommendation. This is where they're actually making a decision. And here, you're actually going to have a space where people are taking a vote, right? How do groups make decisions? They take a vote. Do we invest or not? So that's a very different kind of role, and you're going to use different recommendations. If you've got a group that's generating information, let them talk to each other. But if you've got a group that's actually going to take a vote at the end of the day, you have two strategies. One strategy is just don't let them talk about all. Go back to that collected intelligence paradigm that works so well. Gather your votes of independent people. But sometimes it's necessary for other reasons to let people exchange information. Maybe the different group members have different specializations. One person studies consumer behavior, one person looks at competitors in the field, one person does forecasting related to technology. They need to share those inputs. What you want in that case is to prevent the statistical process that leads to convergence of estimates. So you want people to share information without sharing opinions. That's the strategy you want to employ if you have a group that's a decision maker. Remember, again, you want to share information without sharing opinions. So I want to close by remarking that we've got a couple specific strategies I'm laying out in this video from this study, and I want to remind you that Each of these videos has identified a few properties of group behavior and a few unique strategies. And if you want a summary of all of this, go back and look again at the end of the first video. Thank you.